So sample problem 1814 builds on sample problem 18.13. So 18.13 asked us to predict the relative acidity of different salt solutions. And for each of these, we either had both a cation and an anion that contributed negligibly, so it was a neutral solution, only the anion that contributed, making it a basic solution, or only the cation that contributed, making it an acidic solution. So we build on that with sample problem 1814 in the situation where we're actually going to see here, we'll run through kind of this same thought process. We're going to have both the cation and the anion have the potential to contribute to acid-base kind of changes in the solution. So then the question is, who wins, right? And we asked this question in class, and then the answer was, well, we just walk away because this problem is too complicated. No, it's actually not too complicated, because what you can do is you just need to ask, is the molecule that's acting as an acid a stronger acid than the molecule that's acting as a base? Who's ever stronger wins out. And again, we'll walk through and kind of review how we figure that out. But keep in mind, I am going to only be asking this kind of a problem qualitatively. It's a fairly involved problem if we were to ask this and think about this quantitatively. So let's treat this problem just like we did all the salts from sample problem 1813 and think about what happens when we dissolve this in solution. So we've got zinc formate that we dissolve in water, okay? And that's going to make zinc ions and formate ions. So again, we need to think about the acid or base potential of each of these. So thinking of this guy, acid potential, well, it's a highly charged metal. So it does have the potential to contribute and make the solution acidic. And if we were to think about kind of the chemical equation for what happens, we've got zinc, like our other highly charged metals, likes to complex to 6 waters, having a +2 charge. If we have some water that's in solution, one of those zinc ions gets to give up its proton and become hydroxide, making this a +1 charge, and then generating some H3O+ in solution. So again, making H3O+ in solution is going to make that a solution slightly acidic. But let's think about this guy, right? So if we want to think about whether that has any base potential, we need to look at the conjugate acid. So here's the conjugate acid. Well, and it might be a little bit difficult to think about what's going on unless we were to draw out a chemical structure for this. So here's this guy. Here's this guy. You know, you might question, well, could this act as both an acid or a base? Because what about that hydrogen? That hydrogen's attached to that carbon, so that's not what we call an ionizable hydrogen. What we do have, though, is we have a conjugate acid that is a carboxylic acid. So this conjugate base came from a weak acid, which means that this is a relatively strong base. And so it has the potential to make the solution basic. And if we kind of draw and think about the chemistry that's available here, we've got HCOO-. If it finds some water in solution, it's going to grab that proton and then leave behind hydroxide. And in leaving behind hydroxide, that makes that solution basic. So the big question is, who dominates? We have one guy trying to make the solution acidic, pH less than 7, one guy trying to make the solution basic, pH greater than 7, so who dominates? Well, we have to compare the equilibrium constants to figure that out. So again, this problem didn't give us any pieces of information here. So what we actually needed to do is you need to find, okay, those pieces of information from Appendix C. Okay, and what we can do here is we can look up for zinc. Okay, so here's zinc. So here is the Ka, the dissociation ionization constants for some hydrated metals. So the Ka for this is 1 times 10 to the minus 9th. All right, so we know how strong of an acid that is. Okay. Now, if we look up, here's some Kb values, and these are all alphabetical, Kb, all these are all amines in here. I don't see formate. Well, what I have to do is realize I can look up formic acid. Here's formic acid. Formic acid has a Ka of 1.8 times 10 to the minus 4. So the Ka for formic acid is 1.8 times 10 to the minus 4. Remember, we can use the relationship that Kb is equal to Kw over Ka to get Kb equal to 5.6 times 10 to the minus 11th. So now we just compare the absolute values of those numbers. This guy is a stronger acid than this guy is a base because that equilibrium constant is larger. So we just need to find the larger K value. So zinc is a better acid at contributing to the decrease in pH than formic acid is at increasing the pH. And that's because this Ka is greater than the Kb. Ka being greater than Kb means the solution is going to end up being acidic. Now again, I'm going to let you know that this would be complicated if we did it quantitatively. We are not going to do that, right? Because you'd have to consider how much does this guy contribute to the acidic nature, and then how much does this guy take, 2 steps forward, 1 step back to make it basic. Fairly complex quantitatively, nothing that we're going to be doing here in general chemistry.